Now we are going to discuss application of total internal reflection and its presence in nature. Total internal reflection in nature and its technological application. And this diagram, this image is a device used in endoscopy. Okay, medical students must be knowing about all this. It's to see internal organs, like they insert a tube, a pipe-like thing through your mouth or nose, and they get images of your internal organs. That is by using total internal reflection. We are going to study this one and some other similar ones. Fine. One practical phenomena, day-to-day life phenomena, especially in hot countries and hot summer days, you see on road, is presence of water. You must have seen that on a highway when you drive your car. If it is a hot sunny day, you see there is presence of water ahead of you on the road. But when you approach that one, that will also goes beyond your reach. This is what we call as mirage. This is very effective, like influential in the desert life, because in the desert you are very thirsty and you see water. And when you approach that one, that will go away. It will always go away from you. That's why in English language they use mirage as something not achievable. If something is not achievable, we say it's a mirage. Don't make your results a mirage. Okay. Now, how do we explain mirage? Mirage is due to atmospheric refraction and total internal reflection combined. This is a diagram. See, the diagram in NCERT talks about a palm tree, because this is very visible in desert regions. There is a palm tree here and there is a person here. Okay. And it's given air is at a uniform temperature. When air is at room temperature, near the ground, refractive index will become constant. I'll clarify. Temperature is uniform. So, refractive index of air at the very bottom and maybe at your eye level or a little higher than that one remains the same. There is no difference. Okay. When there is no difference in refractive index, then there is no refraction. So, light ray from the reflected light ray from the tree will go always straight. So, the person will see that here straight. No refraction, no bending. But what happens if it is a sunny day and the surface is very hot? The surface is hot. So, what will happen if the surface is hot? When the surface is hot, then the refractive index of air varies. So, I am saying that this is a very warm surface. Warm surface, and these regions are little colder. This is warmer and this is colder, relatively. Fine. So, refractive index of air will be different at the bottom and the top of the tree, and at the bottom and the top of the person. This will be different. Okay. Now, you can consider air to be having different layers like this, something that we discussed during sunrise question. You can see light, you can consider air as different layers. Okay. Now, the warmer air near the ground will become a rarer one because its density become less. So, its refractive index also become less. You can see refractive index decreasing. That means here higher refractive index, denser medium, here lower refractive index, rarer medium. From top to bottom, refractive index is decreasing. Now, think about a light ray which is coming in this direction. This light ray is coming from denser layers to rarer layers. So, there is a very good chance of total internal reflection. What are the two conditions for a total internal reflection? Condition number 1, it should go from denser to rarer. Second condition, it should go at an angle greater than the critical angle. So, somewhere here at this point, maybe at the first point, it wasn't at a critical angle or less than that, it was less than that. Okay. So, here the angle was less than the critical angle, there was refraction, but somewhere here along the path the angle can be greater than the critical angle, then the light will not go to the rarer medium, this will return back to the denser medium. In short, air is warmer near the ground, colder above. any layer above is denser and layer below is rarer. So, when light comes from denser to rarer medium, there is a chance of total internal reflection, and this diagram shows you that light is totally internally reflecting at this point because the angle of incidence is greater than the critical angle at that point. So, what will happen? This light ray, instead of going straight, will bend and reach this person. Now, think about a situation, if this variation of refractive index were not there, what would have happened? This light ray would have gone to ground here. This person wouldn't have seen it. But due to total internal reflection, it bent and reached this person. And for our eye, the bend in between the path is not understood. Our eye or our brain senses this as if it is coming from a straight point somewhere here. So, this point from where this light has came will be seen here by this person. Okay. So what? Now, all the light rays will not undergo this phenomena. Large amount of light will directly reach this person and he will see the tree. But a relatively small amount of light will undergo total internal reflection, and that will create an inverted image here. So, the inverted image will not be as bright as the object. So, you see a bright object due to direct vision and an inverted image due to total internal reflection. And moreover, the variation in temperature will always keep the refractive index varying. As a result, this image will be a shaky image. It will be shaky. See, you have an object and an inverted image just below that which is shaky, and our brain will sense this for the presence of water, because that is the only possibility. That's what we have been used for, right? So, this will give you a shaky image here and a strong solid image here. This is inverted. So, our brain will identify this as presence of water or some kind of liquid. Fine. This is the explanation to mirage. And I will tell you one more point. What is that? What will happen if the person approaches the tree in search of water? If he approaches, then what happens? Then the light ray which was totally internally reflected will not reach this person. It will go elsewhere. This person will receive only the straight direct light. So, for him, for this person there is this shaky image, but for this person there is no shaky image. So, this will disappear. But from another tree here, the light ray will reach this person and he will see the shaky image below another distant tree. So, as he approaches this phenomena, the phenomena will go away from him. So, the shaky image of the first tree will disappear and that shaky image will shift to another tree. So, as you approach that one, it will go away. That is why we use mirage as a very negative meaning in literature. Mirage not achievable. But if in board exam mirage comes, it should be achievable for you. Study this explanation by drawing the diagram. Now we are going to compel a prism to do the work of a plane mirror. Compelling a prism to do the work of a plane mirror, because you must know a plane mirror, you have a plane mirror like this. This is the non-reflecting side, this part is the reflecting side. What will happen if a light ray falls on a plane mirror like this one? It can reflect to this side. By adjusting the angle, you can actually make it reflect like this, and if you have one more light ray, this can also get a reflector. You can make a light beam bend by 90 degree using a plane mirror. Okay. The same thing can be done using a prism and using total internal reflection. This is a glass prism placed in air. So, this is glass in air, and for glass air interface, critical angle is approximately 42 degree. We saw this in the previous slide. Critical angle is approximately 42 degree. Now assume that there is a light ray A which is falling and reaching this point here. What will happen? This is normal incidence. So what will happen? Light ray will go straight without a refraction. Normal incidence will go straight. But this will hit this inclined surface. And you can see the prism has got angles 45 degree, 45 degree and 90 degree. Now I need to find out the angle of incidence here. I did a normal at that point, and I know that this angle is 45 degree, this will be 90 degree, so this will be 45 degree, this will be 45 degree, this will also be equal to 45 degree. So for this light ray here, angle of incidence is 45 degree. Is that okay? Angle of incidence is 45 degree. Once more, this light ray falling at this point, do a normal, find this angle, and by geometry this angle is 45 degree. Light is now trying to go. See, here light was in air, this was air, this is glass, and here outside again you have air. This light ray is trying to go from glass to air, which is denser to rarer. So there is a chance of total internal reflection. And what is the critical angle? I told you critical angle is approximately 42 degree. Now incident angle how much? That is equal to 45 degree. So the condition satisfied, critical incident angle is greater than critical angle, which implies that total internal reflection will take place. So what? Light will not go out to air, rather this will reflect in this direction, making equal angle of 45 degree. So the light ray which is hitting here, instead of going to air, will go back to glass, and that is at 45 degree. And when it is coming at 45 degree here, this is normal incidence, so the light will go straight out. So I discussed what is critical angle here, approximately 42 degree for glass, and I calculated from the geometry the incident angle, I got it as 45 degree. So the condition for total internal reflection satisfied, going from denser to rarer, greater than critical angle. So this will undergo reflection, and here this will go normal incidence, will come out. So the light coming from point A of your object will come here at A dash. Similarly, light ray coming from B will come here, will undergo this phenomena, will come out here. So if you place a screen, you can get an image here, and that image you can see size of image has not changed. The height of this image and the size of this one are equal, but it got an orientation, 90 degree deviation. Light which was coming like this went 90 degree. That's why we say prism designed to bend rays by 90 degree without changing its beam size. This is by using total internal reflection. So this is a totally internally reflecting prism. And where is this useful? Though this is not part of your syllabus, you should know there is a device called periscope. There is a device called periscope which is used to see objects on the surface of water by watching from inside water. They used plane mirrors here, where light will come here and go like this. So this kind of a bending can be done by using a prism. In binoculars they use this, because when light is reflected by a plane mirror, there is a lot of energy absorbed, but light reflected in total internal reflection, energy absorption is very less. So this always gives you brighter, clearer images. Advantage of total internal reflection over ordinary reflection, energy absorption is less, so images are clear. That's why in many devices they use this kind of prisms. Next one, based on the same idea, you can have prism designed to bend rays by 180 degree without changing the size. I'll explain it in the same way, because this part is exactly the previous one. You can see light coming in this direction, hits here, comes here, and the second point you can see the critical angle. The second point here, the critical angle. you draw the normal. This light ray is incident here. This can be proved to be 45 degree, which is greater than critical angle of glass air medium. So this will not refract, it will reflect in this direction. Normal incidence, it will come out. So the light ray which was going from the point A of the object will go to this point, will come here, will go back. Similarly, light coming from B will go here, total internal reflection, again total internal reflection comes here. So suppose your object was like this upward, the image will become inverted. There is an inversion. There is inversion, no change in size, no magnification, but you can see the light got bent by 180 degree. In binoculars they use this. Okay. Next one, similar phenomena. You have an image AB, you have an object AB, and you need to get an inverted image here. In the previous case, we got an inverted image. I hope you remember that one. In the previous case, I kept an object like this one. I got an image here, but that is by bending it by 180 degree. But here, there is no change. The light is going from left to right. Here also is going from left to right. There is no deviation. No deviation, but there is an inversion. Prism designed to invert image without changing its size, without any deviation. This is again based on total internal reflection. I will explain this. On the first surface here, on the first surface you can draw a normal, you can find out angle of incidence, and this is going from air to glass. So no chance of TIR. This will refract through some angle, this will hit this surface. And here you can see this is the angle of incidence. This is trying to go from glass to air, denser to rarer. So there is a chance of TIR at this point. If this angle is greater than the critical angle, the light will not refract, it will totally internally reflect here, then this can go out after the second refraction. Similarly, light coming from point A, ordinary refraction, total internal reflection, ordinary refraction. So this is normal refraction, this is TIR, this is where you have TIR, then this is again normal refraction, you get it. So light coming from B reaches bottom here, light coming from A reaches the top here, so you get an inversion in the image. The object was like this, but the image will be inverted out there. So these are the three types of totally internally reflecting prisms. 90 degree, 180 degree, and this is a inversion without deviation. All useful in different optical instruments like periscope, binoculars, telescopes, all those things. They say diamonds are forever. Diamonds sparkle, they have brilliance. Diamonds are costly, a very attractive gift item. Okay. Why do diamonds sparkle? Do they produce their own light? Diamonds are just like any, just like a glass piece. It does not produce its own light. But once light enters diamond, it creates a beautiful brilliance, sparkling. This is due to total internal reflection. Okay. Brilliance in diamond is due to total internal reflection because the refractive index of diamond is much higher than other media. Refractive index of diamond comes in the range of 2.4. Glass it is only 1.5. Therefore, critical angle for a diamond comes around 24 degree, approximately 24 degree. For a glass it's around, for water it is around 48 degree, glass it's around 42 degree. So due to the small critical angle, one light ray entering diamond can undergo multiple total internal reflection. One light ray entering can undergo multiple total internal reflection. This will illuminate every surface because when light falls at this point here, this surface will get illuminated. When it falls here, this surface will get illuminated. When it falls here, this surface will get illuminated. So everywhere there will be illuminance created inside the diamond. This will make it very shining and bright. By properly cutting the sides, you can have more number of TIR inside. So a diamond cutter polishes the sides, cuts them properly so that a single light ray can undergo multiple number of TIR. This will make it all bright. That's why diamond sparkle. They do not produce their own light, but they can trap a light and get illuminated. Okay. Next one, medically very useful, technically very useful for all your internet applications, the future world of computers. Optical fibers are very important. Optical fiber again uses total internal reflection. An optical fiber has got a special structure. It has got a structure of, if you see from the side, it has got an internal core. This is called an internal core, and outside there is a cladding. The outer one is known as a cladding. Both are transparent materials, inner one and outer one. So the cable will run like this. This is the cable. Okay, cable. The core has got a higher refractive index, and I can say N1 here and this is N2 here. The core has got a higher refractive index than the cladding. You can see from this diagram, this is the cladding. This portion is the cladding section. This is the cladding around the cable. This has got a low refractive index and the inner one has got a high refractive index. So what will happen? A light ray which is entering one side can go inside this. Now here, this is a denser medium. The lower refractive index is a rarer medium. So it is going from denser to rarer, condition for TIR 1. Second point, suppose that you draw a normal, this angle which is the angle of incidence in the denser medium, suppose that angle is greater than the critical angle for this media, what will happen? The light will not go outside, it will get reflected back to the same medium. And this can fall here. Here again same phenomena can take place. This will go up here. So it can go through the cable multiple. After many number of total internal reflection, light entering one side can come out the other side. So optical fiber uses total internal reflection. It has got a denser core and a rarer cladding. Light can travel through the cable even if it is in a bent form. It can travel after multiple total internal reflection, and I told you before, energy loss in total internal reflection is very less. So almost all of the light, more than 95% can reach the other end even if it is got a length of 1 kilometer. Oh my God, think about that. You shine light here and the same light will be available even after 1 kilometer with less than 5% loss. Ordinarily this is not possible. So optical fiber cable is very useful in many areas, such as they are used for transmitting and receiving electrical signals converted into light. See, in your computer we have electrical current signals. This can be converted into light signal and transmitted through an optical fiber cable. In cable TV that happens. They transmit that through optical fiber cable after converting that into light. Sometimes you can create optical signals directly and you can transmit them through the optical fiber cable. Third one, very important for medical students, all medicos use this. They call it as a light pipe because it can carry light just like a pipe carry water, and that is used in visual examination of internal organs in endoscopy. So total internal reflection is a beautiful one, useful one, entertaining one, and technologically very useful. Study thoroughly with interest, with some personal care.